Hey everybody! The purpose of this video is to get you some an explanation from the quiz on the constants of the first difference. We call it the slope with linear models, but I wanted to make sure you knew mathematically why the slope is always constant. A lot of people just say, well, that's just what lines are, is they tilt the same, and that's, it's a great way of thinking about it, but mathematics generally requires more of proof for things like that. You can't just say something is. And in class we looked at some examples, right? We threw some equations up on the board. I said make up a linear model, and then we examined it, and it worked for that example. But making something work for one or two or three examples doesn't mean it's going to work in general. It just means it works for the ones you've picked. So in this kind of illustration, we're going to make it work in general. So we're going to start with all x values, and we're going to analyze all the y values of the form that look like lines. So I went with mx plus b because I think that's the one you all seem to like the most, mx plus b. I don't know why it's m, but... And to look for x values, it has to work for all x values. What I'm going to do is I'm going to take a subset of x values. We'll start at negative numbers, -3, -2, -1, 0, 1, 2, 3, 4, and then keep going. And we're going to see the pattern that exists from this the pattern that exists here for this pattern here. So notice these are all up by 1. Up 1, up 1, up 1, up 1, up 1. And we're going to come back to that. Okay? So I'm going to put a little up 1, up 1, up 1. So we've taken the entire set of integers and broken it out so that we've got them in line, getting bigger by 1 each time. And the dots above and below just mean this continues forever in any direction we want. We're going to analyze the behavior of the y values over those x values and realize that that behavior, if it's consistent, will continue in either direction, up or down, depending on what we want. Okay, so what we're going to do, for starters, is I'm just going to run those x values into this equation. I'm going to let the y value just be y, and then I'm going to change all the x's to this. So this first one, if you stick -3 in for x, you're going to get -3m plus b. And that's all you get if you stuck -3 in for x. I hope you don't mind, I put the -3 out front as opposed to in the back, because it looks kind of weird having m times -3 plus b. Although that's how you would actually probably do it if you had numbers for m and b, which is what we were doing in class. Quite a bit, actually, with the light bulbs and the V6 and the hybrid engine. We were multiplying quite a bit by that. But here, we're going to leave m and b there. The next one will be -2m plus b, and then -1m plus b, and then 0m, which would just cancel out and leave you with b, and then 1m plus b, 2m plus b, 3m, and so forth. And then we keep going. 5m plus b, 6m plus b, and so forth. So these are all going up by 1. Those are the differences in the x. So what I want to do now is I want to look at the first differences in the y's. Okay? So I'm going to do first differences. So what I'm going to do is I'm actually going to take, like we did in class, and I'm going to subtract this one. Excuse me. Let me say this better. I'm going to subtract this one from this one. So I'm going to do this one minus this one. Okay? Now in class, it was pretty straightforward. It was pretty straightforward because we had numbers. So they were numbers like 7 and 5, and we just did 7 minus 5 and got 2. But now we've got expressions to deal with. But it's still not that bad. Watch. Okay? So if I do -2m plus b minus -3m plus b. I'm just about out of board. I hope you can follow along with me here. If I look at just that expression, I've got a -2m plus b minus a -3m, which is plus 3m, minus a b, which is minus b. I'm going to grab these leaves and pull them back. This plant is growing much better than I thought it would. So you can see what's going on over here. Okay, now hopefully you're going to notice right now, that b cancels off that opposite of b. And then you've got 3m minus 2m, which leaves you with just m. Now that was a lot of work, but what we just saw was as x went from -3 to -2, y went up m. Y went up m. Now, I want you to think about that. And think about why that makes perfect sense. That's the definition of slope. Slope, m, in this case, is the rise over the run. If the run goes 1 unit, then we need to go up whatever the slope indicates is. So if the slope is 2, it's going to go up 2 for every 1. If the slope is a half, this is where it gets interesting, for every 1 it's going to go up a half. If the slope is negative, that could be a negative number. That could very well be a negative. I know it looks like m, but m might be negative. That would just mean for every 1 run, we're going to drop a certain amount. But it's constant. It's a constant m. Now, what I'm going to do is I'm going to erase all that work and just put m here, because we're going to do the work again on the next one. Okay, you ready? Minus 1m plus b minus the whole thing minus 2m plus b. Leaves are always kind of in the way over there. Okay, again, mathematically, minus 1m plus b minus a negative 2 is plus 2m minus b. The b's are going to cancel. And you're left with minus 1m plus 2m, which is plus 1m. Once again, we once again have plus 1m. And no matter how many times you do it, it's going to be just m. I know what some of you are thinking. You're looking at this and you go, but there's no m here. Ha ha! Your little situation breaks down. Let's take a look at it, shall we? Let's take a look at it. And you might say, there's no m here. Okay, I buy that. So that means we just have a b. So we're going to go b minus this. That means b minus a negative 1 is a positive 1. That's plus m minus b. And look what happens. You're left with m again. And no matter what you do, all the way down, the change is going to be m. The change. This one's the nicest one of the whole lot right here. You do 1m plus b minus b. 1m is left. But it doesn't matter. You're always going to get m. You're always going to get that slope so long as these are changing by 1. You can make them change by any number you want. If you make them change by 2, then you'll get 2 m's. So if you jump from negative 3 to negative 1, you'll jump from this m to this m, which means you picked up another m, which means you went 2 m's. You can go half. You can go negative 3 to negative 2.5, which would be half of an m. The relationship is sound. I just think it's easiest to go by 1. And that will work for any linear model, whether it's the light bulbs, whether it's the water heaters, whether it's the solar panels, whether it's the Ford Escape, whether it's whatever else, whatever other model you're looking at. That constant slope is why the first differences are uniform, top to bottom. And this will continue upwards and backwards. So I guess I should put dot and dot 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 there to make everybody all happy. Okay, so that explains why your linear models have a constant first difference. What you'll look at next, and what the quiz is for y'all, is to look at why quadratic models also have a constant difference. Not the first one, but the second one. We'll take a look at that in your quiz.